It's my pleasure to welcome Felipe Zola, who will talk about generative adversarial networks. So Philip was a graduate student in this department. He says that when he took this class or attended this class, it was about 20 people. Now this is twice bigger than when I took this class, which was 2004, 2003. Back then we had about 10 people interested in statistical learning. We had a very small room with one round table, and we're just sitting around a table. Okay, so he then went on to Berkeley for a postdoc with Alyosha Efros. Then he went to OpenAI, and he's done wonderful work in the generative arena and applications to vision, split brain, and all kinds of cool things. And I'm sure he's going to show you really nice demonstrations.
Thank you for the intro. Yeah, so it's great to see how much this course has grown. All the ML courses are now just so popular. It's really amazing. And they should be. Okay, so I'm going to talk about GANs, generative adversarial. You guys have probably seen or know about the problem of image classification, where you have a classifier, let's call it just a black box for now, and it takes in an image X, and it tries to predict a label Y. We're going to be thinking about image generation, which is just the other way around. You take in a label or some kind of indicator of what you want to generate, and you want to make an image of a fish. So this is called a generative model, and the kind of definition that I'm going to be using in this lecture is that it's just a model of high-dimensional unobserved variables. So it's a model of probability of X, where X is some very high-dimensional data, and it might or might not be conditioned on some observations. And GANs are really popular, so I bet a lot of you have already heard about these or seen generated images. And a lot of people have the question, what's the point? We can make like funny-looking cats, but what is that useful for? And I want to show that it's useful for a lot beyond. It's not just about randomly sampling images. In fact, I think generative models are kind of the superset of all probabilistic and modeling questions, all kind of prediction and inference questions. So they're a super important topic. I'm not going to do a lecture on generative models, but I'm going to specifically talk about GANs. But I do think that the broader topic of generative modeling is one of the most fundamental and exciting. Okay, so let's really quickly look at a couple kind of flavors of generative model just to get a sense of the types of problems we're going to be tackling. So in one setting, you are tasked with just predicting an image from nothing, from noise, random noise. So you want to make up random images from scratch. This is the usual setting that people spend a lot of time exploring because it's kind of a canonical fundamental problem, not because it has necessarily that many applications. The applications tend to be more like conditional generative models, where I want to, say, make up a random picture of a bird. An artist might want that. Or you could type in a sentence and say, make up a picture of a yellow bird on a branch. And the setting that I'm going to be mostly focusing on is the conditional prediction problem, where our inputs are one kind of high-dimensional data, in this case an image, and our outputs are another kind of high-dimensional data, some kind of transformation of that image. For example, predict the colors of this black and white photo. Okay, so I'm going to go through three sections that are three different perspectives on GANs. And I'm doing this a little bit in a different order than these were historically covered. The first perspective I'm going to give is GANs as a structured prediction problem, in particular the GAN objective as a type of structured objective or structured loss function. Okay, next I'm going to talk about GANs as generative models. This is the classical way GANs were developed. And finally, I'm going to talk about GANs as a way of mapping between domains or between sets. It's a kind of supervisory signal. When you have supervisory information of the form, I have items in one domain and I want to transfer them to another domain, GANs are a model that can perform that transformation, that mapping between different domains. Okay. And number two is the one that most is most classically presented as what a GAN is. It's a generative adversarial network. But I actually think 1 and 3 are, that's where I've done more work. Okay, so let's think about GANs as structured losses. And we're going to be looking at data prediction problems. These are sometimes called structured prediction, where instead of predicting a single label, like is it a cat or a dog, we're predicting a whole array of labels. We're modeling high-dimensional output data. There's a lot of classic problems that fall in this category. So I'll mostly talk about vision problems. In vision, we have the problem of object detection and per pixel labeling. So here we want to predict for every single pixel in that image, what is the object class. So pink means I've predicted that it's a horse, and other kind of lighter shade of pink means it's a human. There's other problems like edge detection. This is, again, a structured output because the edges have this particular structure. They tend to form lines. I'm predicting a whole image. I could map from a sentence to a photograph, a prediction of what that sentence is describing. I could predict the future. I could take a video frame or current frame of my experience with the world and try to predict what will happen in 10 seconds. Okay, so this is a very generic setting where we want to make high-dimensional predictions. We want to predict raw data, not labels. Okay. So there's two really big challenges in this setting compared to the more familiar setting of like regression onto a single random variable or prediction of a class label. One is that the output is this structured object. So we have a joint distribution over output random variables, which is highly structured. And two is that there's often a lot of uncertainty. If I'm trying to predict the future, there's many possible futures, and they might all be equally likely. And I want to be able to model that type of uncertainty. There could be this kind of multimodal type of uncertainty. Or in the colorization problem, if I have a black and white photo of a shirt, it might be equally likely that it's a yellow shirt, a red shirt, a blue shirt. I have no way of knowing, and I need to be able to handle all of those possibilities. I want to be able to model this kind of multimodal distribution over possible outputs. Okay. So we're going to see how GANs are useful tools for dealing with both of these problems. More generally, generative models are useful tools for handling problems of this nature. Okay, so properties of generative models are that they're built to model a high-dimensional structured output, and they naturally model a whole distribution, a whole posterior distribution, or they model multiple possibilities as opposed to just making a single prediction. Okay. Okay, so I'm gonna talk about this one line of work on the problem of what I call image-to-image translation. So you have an input, you have multiple views of the world, like the black and white view, the color view, maybe the normal map view, maybe the semantic label map view. And these are all different kind of languages for describing the underlying physical scene. And we want to be able to translate between those different languages for describing it. Okay, so this is a prediction problem from pixel input to pixel output. And this problem we can tackle with the kind of familiar framework that I think you guys have seen in this class, which is empirical risk minimization. Okay, so we have a couple different pieces. We have our mapping function that maps x to y, and that's usually a neural network these days. So in all the work I'll talk about, it will be neural nets. That's not terribly important, actually. It could be a different model. We're not going to be going into the details of that neural net. Well, we will a little later, but for the most part, we're agnostic to that choice. Okay, and then we have the objective function, which is what does it mean to make good predictions or bad predictions? And a lot of work focuses on the mapping problem and the optimization problem, but I think actually the objective function and the design of that objective is at least as important, maybe even more important. And as a reminder, the reason we can perform learning problems like this and make accurate predictions of the colors is because we're in a supervised learning setup where we have many, many examples of black and white images and the corresponding color values in those images. And we can learn the implicit mapping in all of those examples by minimizing our error or our loss across many random examples, taking expectation over XY pairs. So this is the paired data supervised learning setting. Okay. And so the mapping is kind of like how do I make those predictions, but an equally important question is this loss function. What should I even be doing? Should I be predicting colors that are close to the ground truth? Should I be predicting bright colors? What does it mean to make a good prediction? Okay, so let's walk through this and see what happens if we do something kind of naive. We do the kind of most basic loss function, the least squares loss. Okay, so this is, I think you guys have seen things like regularized least squares or just least squares regression, where we want to predict values that are as close as possible to the ground truth colors in a Euclidean distance sense, which is described on the bottom there. Okay, so if we do that and we train up an algorithm to do this, we get predictions that look like that. So this is a kind of, sepia-toned image. It's not what we want. This is the real ground truth. It's this bright yellow bird. Okay, so it didn't actually work very well. So let's try to understand why that's going on. If I look at a little bit of the plumage of the bird up here, it might be that this is a bluebird. Maybe there's some examples of bluebirds in the data set. And maybe this bird actually comes in two varieties. Maybe it's equally likely to be red or blue. Okay, so if there's two possible, equally probable colorizations of a bird, does anybody know what the least squares minimizer will be? Yeah. What's that? Purple? Yeah, so it'll be the average of the two. The minimizer of the least squares objective, the best estimate in a least squares sense, is to average over all of the plausible outputs. It's the average of the probability density function or the posterior distribution. Okay, so you probably have seen this in the context of least squares regression on like fitting x to y, fitting lines. You kind of regress to the mean. But this is, in vision, it shows up as this problem where you get averaging over all of the plausible outputs. And in colorization, that means you get grayish images. Okay, so we worked on this project a couple of years ago. This was a project on image colorization. And we came up with a specially designed engineered loss function that would avoid this averaging effect. And so we got nice, colorful images. And we designed our loss function to encourage colorfulness, in fact, to encourage rarer colors to be overrepresented. So it's not the yellow bird, but we thought it looked cool. And we were pretty happy until we went and tried it on some simple images like this one. Okay, and it starts scribbling bright pinks and blues and reds all over the place and yellow. We even put this online, and people got really upset about this because there was this bot on Reddit that would colorize their photos, and it would always scribble yellow all over it. So it became kind of a joke. So we were sad. And I think the lesson here is the lesson from King Midas. King Midas was granted a wish, and he wished that everything he touches turns to gold. And that seemed really good until he touched his food and couldn't eat, so he starved to death because the food turned to gold. So you have to be careful what you wish for. The loss function is how we tell our learner what we wish it to do. And it's really hard to design good losses. There's a related problem in reinforcement learning, which is it's hard to design good reward functions. And there's another related problem in economics, which is it's hard to design good incentives for an economy. So this problem of designing good incentives, reward functions, cost functions, loss functions is all really the same. It's a hard engineering problem. It shows up in vision all over the place. If I want to do colorization and I do least squares regression, I get grayish images. If I want to do super resolution, predict the high frequencies from a low frequency image, and I do least squares regression, I get blurry images. That's because I'm averaging over all the possible high frequencies, and averaging is like a blurring filter. So people have done this thing where you have a grad student who does grad student descent on this, and engineers especially designed loss function that will solve the problem and make the thing look good. But we don't want to do that for every single problem. There's so many of these problems. It'd be great if we could have some automated or universal design of objectives or loss functions. Okay, so here's where we get to GANs. Well, one trick that we can do is we don't know what it means for a photo to look good, but we can precisely define what it means for a photo to look real. Because we have examples of real photos. And what it means for a photo to look real is that it's indistinguishable, or the outputs of our model are indistinguishable from real photos. Okay, so this is the idea of a GAN, and I'm going to go into the details of how it works. We have a classifier that tries to distinguish between generated photos and real photos, and scores us based on the realism of our generated photos. So this is a way of predicting things that look like real photos, that look real. Okay, so let's look at how that plays out in the colorization problem. We have our input x, which is a grayscale photo. We have our mapping function, which is going to be a neural network, G, which we call the generator. And it predicts an output g of x, which is a colorized photo. At the same time, we're going to introduce another neural network, which is going to model the quality of the output. So our loss function, our cost, is going to be modeled by another learning network, D. And D is going to predict, is the output a real photo or a fake photo? And these two networks are going to play this adversarial game. So G tries to synthesize fake images that fool D, and D tries to identify fakes. And they fight back and forth in an arms race. So G is making more and more realistic fake images. D is getting better and better at identifying any little artifact, any little error in the output. And eventually, G makes perfectly real images. So mathematically, we have our training set of black and white color pairs. We're going to do empirical risk minimization on this training set. So we're going to try, so let's look at the learning problem from the perspective of the discriminator. Okay, so it looks like this. When we see a fake image, an image generated by G, so when we see a G of X, we should classify that as fake. So we can think of D as a classifier that tries to assign high probability of being fake to fake images. So we want to maximize our log probability, so maximize log D G of X. If we see a real photo, we want to say low probability of being fake, so we can maximize 1 minus D, which is modeling the probability of being fake. Okay, this is just a binary classifier. This is just kind of a logistic regression. Okay, so at the same time, G is going to do exactly the opposite. G is tasked to make the score of D be as low as possible. So G tries to minimize the score that I showed in the last slide. We can then optimize G by doing backprop or gradient descent. And we will update the parameters of G, where G tries to make outputs G of X that look more real according to D. Okay? And if we do this in a way where we fool the best possible D of all functions we could possibly conceive of, then I'll show a little later that in that setting, G is making perfectly realistic images, which means it's making samples from the actual data distribution, or that are indistinguishable from the data distribution. Okay. And the perspective in this section of the talk that I'm taking is that D is kind of like a loss function. D is a scoring function that scores the quality of the output of G. But rather than being a hand-designed loss function, where we had to toil in lab, twiddling little knobs here and there, we automatically designed that loss function as part of the learning problem in order to satisfy this meta objective of the adversarial game. Okay. So this one problem that I glossed over, which is, what if G takes in this photo of the bottles and produces the cat? Is that cat a real photo or a fake photo? Okay, who thinks it's real? Not too, whoa, okay. Who thinks it's fake? Okay, well, it's a real photo. I'll say that. This is actually the cat Aquarius, who was my co-author's cat on this project. And it's a real photo, but we left out one thing, which is it's not the color. You would never see a photograph that has the color channels of a cat and the grayscale channels of bottles. So this color grayscale pair is an unrealistic color grayscale pair. So really, we want the discriminator to look at the pairing x comma y rather than just looking at the output g of x. So we can do that by just letting our discriminator observe the grayscale channels and the color channels, and it can check whether the color channels are correct and if they match the grayscale channels. Okay. So this is a fake pair. We'll update our parameters, and we'll make something that looks perfectly realistic, cannot be distinguished from real examples of grayscale color pairs. Okay, so this is the full GAN optimization problem. In particular, I'm showing a so-called conditional GAN, where I've conditioned on the input X. One trick that you can use to make this the training faster and more stable and robust is, well, we're in the supervised learning problem setting where we have paired data, input X, output predicted colors. So we can mix our GAN objective with something more traditional, like just doing least squares regression or L1 regression, which is the same as least squares, but using the absolute value as opposed to the squared distance. And if we do least squares regression, I already told you it makes grayish images. But if we just add a little lambda plus our least squares regression, it kind of stabilizes the GAN optimization problem without sacrificing much quality in the output. So it's kind of a middle ground because the GAN minimax problem can be hard to optimize. Okay, so that's just a little trick. Stable training, fast convergence. So we can use this framework to predict the colors in photos. Here are some predicted results. But the real power of this is you can apply it. There's nothing specific to colorization. I could have applied it to basically anything where I have paired training data of input examples and output examples, right? So this was a friend, Chris Hess, took our code and made this cool online app. You guys might have tried it or want to try it, where he trained the mapping from edge maps of cats to photos of cats. And then you can sketch an edge map of a cat, and it will predict the photo. Okay. So yeah, people went kind of crazy with this online. Yeah, I don't know. Okay. So that's the exciting thing about GANs as structured prediction is that they don't have to be engineered to the particular problem. This is an objective function that applies to a huge class of problems. And this is true of any generative model. Generative models are kind of the complete solution. They're a way of making of learning mappings that are as close as possible to reality in some very fundamental senses. I'll talk a little bit more about the exact kind of fundamental sense of what the GAN is optimizing when we get to the generative model section. Okay, but I want to talk about how this relates to the problem of structured prediction, which is a more classical problem. And let's go back to our super resolution setting. So we have our input X, which is a blurry photo, and we want to predict the sharper image. We want to do super resolution. Okay, so if we do L2 regression and learn a predictor that minimizes the sum of squared errors, we're going to get a blurry output because it's going to be doing this kind of regression to the mean. It'll be averaging between all plausible high frequency mappings, and therefore that averaging will be a blurring operator. But people have come up with ways of solving this. And usually the starting point is that think of it as you're predicting a bunch of random variables. And L2 regression, where you're just minimizing the sum of squared errors, is equivalent to the modeling assumption that every single pixel is conditionally independent of every other pixel given the input. Okay, so it's this modeling assumption here. So this is a graphical model in which we're thinking of all the output variables as conditionally independent of each other. Okay, so because we did not model the dependencies between pixels, we weren't able to model things that are kind of second order effects like sharpness. Sharpness is a kind of second order effect. You can think of it, edges are something that is a change, and sharpness is all about getting the edges in the right locations. And changes require you to look at two adjacent pixels and see how they change. Okay, so people came up with all kinds of fancy graphical models to model dependencies between the pixels in the output of a prediction problem. One class of model is called a CRF, conditional random field. And usually this model will model all of the pairs of pixels. Rather than treating all the pixels as independent, it treats the distribution as factorizing like that. That you can say that the probability density is factors over these cliques of pairs of pixels. Okay, So maybe you've seen graphical models before. If not, basically the idea is that we can model all kinds of higher order interactions and correlations in our output. But it becomes a really hard problem to design those models and to scale them up beyond things like pairwise interactions. So what we really want is to model the entire density of all possible interactions. Third order effects, second order effects, long range dependencies. If there's one eye here, there should be another eye over here, right? Those pixels are really far apart, but we want to model that dependency. And what GANs do in theory, if I have a sufficiently high capacity discriminator generator, I perfectly optimize it, I do everything right, it will really model that full joint distribution. And this is what's so exciting about generative models is if you give them sufficient capacity and infinite data and you satisfy a couple technical properties, then they're kind of the complete solution. It's really hard to design those by hand, so you want to learn those. Okay, but that's not really the full story, because you could say, just put an infinite capacity neural net as D, and then D can model any type of error. It can model if the eyes are misaligned, if they're too far apart, if the edges aren't right, if it's too blurry. It can penalize any error in the output. But we don't have infinite capacity neural networks. In practice, we have to make things tractable. So the architectural design of our function D is going to be how we implicitly define the kind of class of errors that we're penalizing. So it implicitly defines a kind of graphical model or what kind of structure we're sensitive to. And I want to show you that with this example. So rather than having D look at the entire image and say, is it real or fake? And then it could possibly look at if the bottom left pixel has the right correlation with the top right pixel. Instead, D is only going to look at little patches in the image and say, is each patch a real-looking patch or a fake patch? Okay, so I'm going to demonstrate what happens as we grow our patch size. And we're going to look at this problem of predicting the appearance of a facade from a label map of the facade. So this label map, the blue squares are indicating that there's a window, and the green is indicating there's a balcony and so forth. It's like an architectural design. If the discriminator is looking at just one pixel at a time and saying, is it a real pixel or a fake pixel? We get back to our old setting where we don't really capture any structure beyond, we're treating each pixel as conditionally independent given all the other pixels. So we get a low quality image. So the design of the receptive field or the architecture of D is affecting what types of errors we can penalize. The one by one, the discriminator that only looks at one pixel at a time cannot penalize second order effects like edges. So the edges are incorrect, it looks blurry. If we make a bigger discriminator that looks at 16 by 16 patches and tries to say, is each 16 by 16 patch in this image real or fake? Now we capture higher order effects like sharpness. We can make sure that the variance and the distribution of edges in the patch are correct. If we go up to 70 by 70, now we pretty much capture everything. And if we go beyond to a full image discriminator, in this case it's 256 by 256, the quality actually got worse. And one way to understand why the quality got worse, like the 256 by 256 discriminator has the capacity to do exactly what the 70 by 70 did, but it got worse. One way to understand is that the 70 by 70 is a modeling assumption. It's an inductive bias, which told us we actually don't care about effects beyond 70 by 70 pixel receptive field size. So that discriminator has fewer parameters, and it actually has more observations because there's more 70 by 70 patches in an image than there are 256 by 256 patches. So fewer parameters, more observations, and we get a statistical advantage. So there's kind of an optimal size, an optimal architecture of your discriminator, and it's going to depend on the modeling problem that you have. You don't really want to just go to an infinite capacity discriminator that's like the set of all Python programs. That would just overfit, and you wouldn't have enough data to fit that model. Okay. So that was the perspective of GANs as structured loss functions. And they deal with this problem of modeling high-dimensional structured unobserved variables or high-dimensional structured predictions by using a deep neural network or a high-capacity function to model the output. And it's a learned function as opposed to being something hand-designed. OK, so I'm going to move on to the next section, but any questions about that perspective? OK. And feel free to interrupt when, oh yeah, question.
Just to clarify, so talk about the Markov-Random field, but we cannot explicitly use Markov-Random field here in the model.
We don't use, yeah, so that's only a kind of implicit connection, yeah, analogy, yeah. So we're never explicitly using that, but there's a relationship between the kind of things that that models and what the discriminator could, in theory, model. Of course, this is a little imprecise because we don't know exactly what the learning dynamics are. The discriminator, what it actually models is going to be a function of the data and the optimizer, and this is all still not super well understood. Yeah?
Is training GAN slower compared to training other neural networks?
So a really interesting thing about GANs is that training is often faster, actually. And people always think like, oh, to train a deep learning model, you need a lot of data. Well, it's not really true. Depending on what you mean by a lot of data, a single image is a lot of data. So you can actually train, the facade example I showed you was trained on 400 images. Okay, and people have also trained GANs. You take a single texture, you train a GAN to make more things that look like that texture from a single like 1024 by 1024 texture example, and it can make photorealistic samples of more texture. So a single photo had 1024 by 1024 pixels. That's like a million data points. So that's already big data. And they can train really quickly too when you're only feeding them to so few images. Like if you train a classifier to get state-of-the-art results, now people train on millions or billions of photos. And the interesting thing is that a lot of these applications we trained on a couple hundred or 1,000 photos. Yeah. Yeah, OK, so we're going to talk about that in the next section. So I'll get to that just in a second. Yeah.
And how does that compare to prediction clusters or any other intervention model?
Oh, sorry, what was that?
Intervention model compared to other methods like prediction
GANs on edge detection?
Yeah, for edge detection.
Yeah, so I think for a lot of kind of classical problems, GANs are always kind of the second best thing to do. I think people used to say that for neural networks. For any problem in neural network, it's the second best thing to do. Now it's probably true for GANs. Because if you have a specific application like edge detection or object detection, there's a lot of highly engineered approaches where humans have designed the right thing to do. And the GAN tries to kind of automatically do that. And training can be unstable. They're not fully understood. So yeah, they tend to do second best, I would say, on most like narrow problems. But on problems that people didn't have solutions for, like generating photorealistic images, they work really well. On more classical problems, like you could use a GAN to do ImageNet classification. It applies to that setting too. It applies to any setting. But we already had good solutions there that were pretty well designed. OK, let me move on to generative model perspective. OK, so here the idea is rather than predicting like color or some other view of an image from a high-dimensional input, rather than predicting how cats look from a sketch of a cat, can we just synthesize an image wholesale from scratch? Okay? A lot of currently popular generative models take the form of being a mapping from random Gaussian noise, high-dimensional Gaussian noise, so a 100-dimensional Gaussian random variable, to a photo. So GANs are one example. I'm not going to talk about it, but there's a bunch of other ones too. There's VAEs, normalizing flows, autoregressive models. These all have similar properties, but some advantages and disadvantages. OK, so how do GANs do this? Well, it's really the same story as before. We sample some random noise. We pass it through our generator network. It produces g of x, which is we're going to try to make an image. D determines if g of x looks like a real image or a fake image. G tries to synthesize fake images that fool D, and so forth. We backprop the errors, and we eventually learn a mapping from random noise to realistic photos. Okay. But the nice thing about this setting is we can understand GANs to be a kind of implicit generative model, where a generative model is something that allows you to model the joint distribution of some variables, some data X. So the joint distribution of all the pixels in the universe. What GANs do is they don't actually explicitly model P of X. They don't give you likelihoods or they don't give you the probability of an image, but they give you a mechanism for sampling from P of X. So the way that works is you sample from your noise distribution, you sample some random noise, and then you use a deterministic mapping to convert that noise into an image X. And I'll demonstrate that when the GANs are trained, sampling noise plus applying the deterministic mapping G of X is equivalent to sampling from the actual data distribution, P of X. Okay, so that's this property. So GANs are implicit generative models because they allow you to learn a function that samples from the target distribution you're trying to match. P of X would be the training set, which might be all the photos of flowers in the world. Okay. Oh, so let's see what that allows you to do, some fun things. Now I can sample some random noise, and I can start to walk around in Z space, okay? So maybe I'll draw. Okay, so we have our Z space, 100-dimensional Gaussian noise, and we start at a random point here. We can map that to our X space, which is photos. And now we can look at what happens as I walk in a straight line in Z space. What does that map to in X space? It's going to map to some interesting curve. And in the next video, I sampled a random noise, and I start to walk in a line in Z space and synthesize the photos by applying G of Z. Okay. So you get really cool effects. So we've learned, this was trained on celebrity faces, and it's learned a model that can synthesize nearly photorealistic faces. And interestingly, Z space is well organized, which is another nice property of these generative models. The underlying latent space from which you generate photos often has some nice properties, like it's smooth. Okay, here's if you train on ImageNet photos, you can see that it's something kind of okay looking. This paper came out a year ago. One came out about a month ago that is just way better, but I don't have a video like this of it. This is a really rapidly moving field. It's not inconceivable that we'll have like things that look photorealistic, next year when this class is taught. Okay, so let's look at a proof of. This is from the original GAN paper. This is going to be a proof that when the optimum of the GAN objective actually will produce a function that samples from the data distribution, meaning it makes perfectly realistic images. So intuitively, I think it might already make sense. Well, if you have a generator that produces outputs that cannot be distinguished from real photos, then those outputs must be from the same distribution as the distribution of real photos. But let's go through the math. So the first piece that we need is this proposition that we want to know we have this minimax game, right? And if we fix G and we just optimize D, D is trying to detect whether G is making real or fake photos. Well, the optimal D is going to be the ratio of the probability under the data distribution of our sample X divided by the sum of the probability under the data distribution and under our implied generator's distribution, PG. So yeah, I think that you'll probably have to, I'm just going to give a kind of sketch of the proof or go through relatively quickly, but this is in the original paper, and it's a pretty straightforward proof, so I think it's a useful exercise to read it carefully. But the idea is that we can write the GAN objective as such. So this integral is just the expectation over the data. And we're saying we want to maximize the probability log d of x for real data, p data, and minimize for fake data, pg of x. So we want to maximize, d wants to maximize this function v. Okay, so this is just rewriting what I had before. But looking at it this way, well, we see this function has the form a log of y plus b 1 minus b log 1 minus y. And for any function that has that form, the maximum is of the parameters a and b, which are p data and pg, is a over a plus b. Okay, so this is the form of the optimal discriminator. Now we can show that PG, the distribution, so our GAN G of Z is sampling from P of G, and our data distribution we're imagining the world is sampled from P of data. And we want to show that that is the unique global minimizer of the GAN objective. So now we imagine that we're using the optimal discriminator, so D is fixed, and we want to find the generator that's going to try to fool the optimal discriminator. So the cost for the generator, because it's argmin G, max D, VGD. So from the generator's perspective, we're going to be trying to minimize this maximum. We're going to try to say that the optimal discriminator cannot tell between real and fake data. So the maximum discriminator cannot tell between real and fake data. Okay, so rewriting the GAN objective one more time. And now we're plugging in the optimal discriminator D star, which we derived on the previous slide. Okay, so we know the optimal discriminator has that form, P data x over P data x plus PG data, PGX. And the nice thing about writing it that way is it turns out that expectation, if you're familiar with it, you'll see that that is related to a KL divergence. If not, this is a well-known divergence between two distributions, so P data and PG. And in particular, you can rewrite the cost that the generator is maximizing, or sorry, the cost that the generator is minimizing can be rewritten as a sum of these two KL divergences between the generator's distribution P of G and the data distribution P data. The nice thing is when we write it that way, we can see that KL of this plus KL of that has another name. It's the Jensen-Shannon divergence between the distribution P data and PG. And we know nice properties of that divergence. It's non-negative, and its unique global minimizer is when PG equals P data. Okay, so that was pretty quick. I think that I just wanted to kind of give you guys the notion that the global minimizer of the GAN objective is to make samples from the data distribution that you're training against. Okay, and then one reason why it's useful to look at it that way is because it tells us what happens when we have an imperfect model. So imagine that we have some data on the left. It's two Gaussians, and we want to fit a single Gaussian to that distribution. We want to model that data distribution with a single Gaussian. Okay? The minimizer of KL divergence, which is the same as the max likelihood fit of the Gaussian to the data distribution, is to cover both of those two bumps, cover both of the modes. So max likelihood has this property being mode covering. It tries to, under model misspecification, it tries to cover all possibilities, kind of hedge. Whereas the JSD, the Jensen-Shannon divergence, which the GAN can be understood as optimizing, has the property of mode collapse. Under model misspecification, it will try to fit its distribution. If it can only fit a Gaussian to these two bumps, it'll just choose one of them. It'll sacrifice the other. So this is called mode collapse. And this is one way of understanding some of the qualitative behavior of GANs compared to other generative models. A lot of generative models do the max likelihood solution, which is mode covering, and they make blurry images. So this is one other perspective on why you're getting blurry images. It's because you're kind of averaging over all possibilities. And the GAN will just pick one possibility and be really confident about it. So the GAN will make sharp but hallucinated results, and max likelihood models like a VAE will kind of hedge and make blurry results. Okay. Okay, so one other interesting point on GANs as generative models is, well, I told you that the GAN objective is D as a classifier, and this is like logistic regression classifier. But it turns out that we could actually instead say we just want real photos to get a high score and fake photos to get a low score. So we don't need to say that real photos should be classified as real and fake photos should be classified as fake. It's sufficient to say that real photos get a high score in some sense and fake photos get a low score. And that scoring function f now doesn't have to have a log. It doesn't have to be something that's bounded between 0 and 1. It can be a whole variety of types of scores. It could be something that's just, for example, trying to maximize that G will try to make the highest number possible when it sees a real image. And F will just be some random mapping, let's say. And G will be optimized to make F get a really high score when it sees a real image and a really low score when it sees a fake image. And different choices of F imply different divergences. So I said that this GAN objective corresponds to the Jensen-Shannon divergence. Other choices of F correspond to other divergences. One that you may encounter is called the Wasserstein divergence, and that's a popular model called the WGAN. Okay, so just wanted to mention that we can use a whole family of F divergences, not just the logistic classifier. Okay, so now I want to get to the question of, in the conditional setting, how do you make predictions about multiple possibilities? So I told you that we have this idea of GANs as a generative model that can sample from random noise to produce a random photo. But there's another, but how do we use this in the conditional setting where we are mapping from an input, label map X, to an output photo, G of X? Okay, so the stuff I told you about in the first part of the talk only predicted one appearance of the facade. But there's many other plausible appearances. It could be a brick building with equal probability. So the way that we actually get stochasticity is the same trick as before. We just let G be conditioned on X, but also take some random noise as input. And it will learn to map that random noise to use that random noise to sample multiple plausible outputs. Okay, so the kind of full conditional GAN objective actually needs to, G needs to take both X, the data you're conditioning on, as well as some random noise, which will be used to map that data to a random sample from the set of possible outputs. One trick that's important here is that if you just train this as I've shown, usually G will ignore the random noise Z. It won't have a huge incentive to actually use that to make an accurate looking prediction. So oftentimes people will try to get Y to depend on Z by making it so that there's another network that should try to predict Z from Y. So now G is scored for making outputs that are from which you're able to predict the random noise seed. Okay, so in order to predict the random noise seed, the outputs should depend on Z. And that allows you to get, if I use different random noise, I'll get different samples. So I could say this label map could appear as a brick building or a stone building or so forth. Okay, so here we exploited this second property of generative models, that they're a way of modeling an entire multimodal distribution. So you're using random noise, random Gaussian noise, to get stochasticity. G is a stochastic function, and sampling from G should sample multiple plausible outputs. And there's actually a proof that under certain conditions, the global optimizer of the GAN will be that you're sampling from the true data distribution. Okay. So yeah, any questions on that part? And then we'll move on to the last part of the talk. Yeah, question?
Is there any reason that we use the random noise, or learn from mapping between random noise and the actual data distribution instead of we learn the data distribution itself?
Yeah.
Is there any technique?
So let's see. There's other generative models that can fit a distribution differently, where they might look more like they're they're just directly modeling the data X. This is essentially this trick of having a random variable Z and then a deterministic mapping. It's just kind of a convenience that sometimes this trick is called the reparameterization trick, where I've parameterized my model as being deterministic stuff plus random stuff. And this is a useful trick because it allows us to do gradient descent through this deterministic function. And it makes it so that the modeling and the optimization is easier. So that's basically the trick, is to factor your function into the deterministic part and the random part and treat each one separately. But not all models do that. Yeah. Question?
You replaced the population with the empirical, right? When you actually did the optimization with the data distribution.
Yeah, that's right. Yeah.
So the fact that the population is the saddle point for that problem doesn't really imply that you get something. It's not clear.
Yeah. Oh, wait. So, sorry. Can you clarify?
So you
Yeah.
had a proof.
Right.
The saddle point
Yeah.
is with the true distribution of
Right.
the data. But in practice, you have the empirical.
In practice, you have the empirical distribution. Yeah.
It's not clear how
That's true. Yeah. In the limit, so the proof is only for the limit of infinite data. Yeah. And the proof is also for, there's another proof that this thing converges, but it's not actually, there's no achievable algorithm that will get it to converge. So this proof has only limited traction on reality, but it's still, I think, useful as kind of, framing the way to think about it. Okay. Okay, so, oh yeah, one more question?
So you're modeling this P of X by mapping EC to X hat.
Yeah.
But are there any GANs that can give you access to the actual value of P of X, the actual probability of the model?
Right, so yeah, that's a great question. In general, you don't get that, but there are a variety of ways to try to bound or estimate the probability P of X. So one way is you can also learn the inverse mapping. So you learn the mapping from Z to X, but you also learn the mapping from X to Z. This model is called the BiGAN model or the ALI model, approximately learned inference, or adversarially learned inference is the ALI model. And let's see, so in those models, I could take some data point X, I could map them to Z, and then I could measure P of Z, and that doesn't directly give me P of X, but I can do various tricks like the change of variables formula from. So the change of variables formula is saying if I have a deterministic mapping between random variable X and Z, I have a way of estimating the density of X if I know the density of Z. So anyway, there's basically some tricks you can do, but in general, that's an open question and a hard problem. Okay, so last section is going to be one more perspective on GANs, which is that they're a way of mapping between two different sets. So if I have a problem where I have data and some of the data is labeled as being in one set and the other data is labeled as being in another set, the GAN is a way of mapping the data from one set to what it would look like if it were in the other set. Okay, so let's see how that all works. So previously, I was talking about the paired data setting. This is often called the supervised learning setting, where I'm learning from examples. I have many examples of inputs and outputs. I have my example of an input edge map, and the appearance of a cat that has those edges. So the way that we actually got that training data is we applied an edge detector to photos of a cat. Okay? But more commonly, we actually don't have paired data. We don't have input-output examples. Very commonly, we just have many examples of one thing, like many photos of a horse, and many photos of another thing, so many photos of a zebra. But we don't have a horse that's positioned exactly the same way as a corresponding zebra. We don't know the correspondence between the images of horses and the images of zebras. Okay, so here we don't have the usual supervised learning setting. Instead, we could still try to learn a mapping from horses to zebras by reasoning about the kind of stylistic differences between those two sets and say, well, what would this horse look like if it were a zebra? You guys can kind of imagine that. It'd have stripes. Can we make a model that can also imagine that? Okay, this is some work that Jungyan and Taesung did back at Berkeley. Okay, so let's look again at our conditional GAN for predicting the appearance of cats from edges. We took our edge map X, we generated G of X, which is the predicted appearance of the cat, and we did that in such a way that it looks like a real edge map cat photo pair. And that's corresponded to this minimax problem that we've shown several times now. In the setting where we don't have paired data, now we don't know what input corresponds to what output. So we can't create these pairs that the discriminator will try to check if they look like a real pair, because we don't have real pairs. Okay? So we can't use our conditional GAN down here, because notice that D observed both the input X and the output G of X and tried to say, is that a real or fake pair? But we do have something else. We actually do have photos of zebras and photos of horses, and we can go back to the unconditional GAN, where D only observes the output G of X and says, does that look like a real zebra or not? Okay, so now D does not observe pairs and say, is it a real pair or is it a fake pair? It just observes output G of X and says, is that a real zebra or a fake zebra? So this is really interesting because from this perspective, D is not like a normal loss function. A normal loss function is going to somehow measure the distance between the predicted output and the target ground truth. But here, we're only checking if the predicted output satisfies some properties. In particular, we're checking if it is part of the set of things that looks like zebras. Okay, so it's an objective function that doesn't actually require paired data. And I think one useful way to think about this model is I told you that the unconditional GAN is a mapping from Gaussian noise to a target data distribution. It's a mapping from one set to another set. So why can't we just apply the same thing to map from, instead of taking input as random noise, just take input as the set of horses, or the distribution of horses, and that will map to a different set, the set of zebras. Okay? So that's great. We could train this mapping, and you might expect that it would make a realistic-looking zebra, because that's what we're telling it to do, make realistic-looking zebras. But there's a difficulty here, which is that this image X could produce a G of X that looks like the one that corresponds to that image, or it could produce a completely different output G of X. But our discriminator would have to say both of those are equally real zebras. So there's nothing now that will force the output to correspond to the input. We're going to produce realistic-looking zebras, but they're not necessarily going to have anything to do with our input horses. Okay, so we needed to add some constraints because this is a very under-constrained problem. There's so many different ways that the set of horses could map to the set of zebras. We're going to add some extra constraints that will encourage the mapping to be the meaningful mapping, as opposed to a random mapping. So we introduced this in the CycleGAN paper, and there were a couple other papers at the same time, DiscoGAN and DualGAN, which proposed the same thing, the same objective. So here's how it works. We're going to learn a mapping that will map from set X to set Y. So we'll take in a horse photo, and it will produce a zebra photo in order to fool a discriminator dy, which is checking if the output Y looks like a zebra or not. At the same time, we'll try to do the opposite. We'll take in a photo of a zebra and try to predict with another function, we'll try to transform with another function that zebra into a horse, such that the output predicted horse looks like a horse according to another discriminator, dx. And this idea, it goes back to an idea from language, which is called back translation. Something that dates back at least 100 years. Mark Twain was writing about this as a kind of joke, where he translated from English to French, and then he translated back from French to English, and he kept on doing this and created absurd translations. You can do this on Google Translate, it's kind of fun. But the idea is that a property that we want with a language translation is that if you translate from English to French, and then you translate back, you should arrive where you started. In other words, the language translation should be bijective. It should be this kind of one-to-one mapping. So in NLP, people have explored that by this idea of back translation. Translate from one domain to the other and back, you should arrive where you started. And that's the same idea here. We will try to encourage that if we translate from horse to zebra and then back, we should arrive near where we started. So we're going to penalize the distance between where we started and where we ended up. We'll go x to g of x to f of g of x, and we should arrive near our starting point x. And for symmetry, we'll do that in both directions. We'll also go y to f of y to g of f of y, and we should arrive near y. Okay. So one kind of fun perspective on this is that this entire cycle consistent mapping actually looks like something that took a horse image and mapped it back to itself. So a mapping that takes X and maps it back to itself, one such mapping is called an autoencoder. And this is basically an autoencoder in which you have to pass through this bottleneck representation, which is a photo of a zebra. It's a really weird autoencoder where it takes a horse, it tries to reconstruct the horse from a representation of the horse, but that representation is a zebra. Okay. If you've seen autoencoders, it's just, this is actually an adversarial autoencoder, is another name for this model. Okay, but this actually works, surprisingly enough. We can turn horses into zebras. We can turn apples or oranges into apples and vice versa. Sometimes it fails. Yeah. So not perfect. Okay, so we don't actually know why this works. I gave some intuitions that a good translation should be one that's bijective. There's many possible mappings between two sets. The set of bijective mappings highly constrains what we can do, but there are still many possible bijective mappings between two sets. So there's been some recent work on trying to understand why this actually works and makes sense. It's still an open question, ongoing research. But let's try to understand the ambiguity first. So here's a simple example from a colleague, Mingyu. And what this is showing is that if I have two sets, x1 and x2, here's one mapping that is cycle consistent. I can map from heart to upside down heart, to right side up heart, to upside down heart. So x1 to x2 back to x1 arrives where I started. This is cycle consistent mapping between these two domains. But so is this one. Actually, any permutation is going to satisfy our cycle GAN objective just as well. It'll produce outputs that look like x2 and are cycle consistent. Okay, so we have this huge symmetry. The mapping is not at all unique, even though we've already constrained it to be bijective, which is a huge constraint. There's many possible mappings that are not bijective, but there are still many possible mappings that are bijective. Okay. So one hypothesis that people have been putting forward recently is the so-called simplicity hypothesis. And that says that the correct mapping, the one that we humans think is the true mapping, and that maybe actually the true mapping, if there, to the extent that there exists a true mapping in the world, it will tend to be a simple mapping. And one way to understand this is, suppose we're mapping the line segment A to the line segment B. Okay? There's two mappings there's an infinite number of ways of mapping that one line segment to another one, right? I could shift around all the points and expand some points and contract other points. But there's only two that really seem simple. So one is the identity mapping, where that's on the left, you just kind of map in straight lines. And the other is the kind of inverse of the identity. You just, A gets flipped around to create B. And in this paper, what they showed is that for this simple example, if I have a simple neural network, these are the only two mappings that satisfy the cycle-GAN objective that a simple neural network can find. Their simple neural network was some kind of one hidden layer network with linear plus ReLU style network. So they had a very kind of toy class of models, and they showed that that toy class can only satisfy the cycle-GAN objective on this problem with these two mappings. Even though if I were searching over all possible mappings, like I were searching over all possible Python programs that could take a line segment as input and produce another line segment as output, I could have much more complex mappings, constrained to the fact that I'm only looking at a very specific hypothesis class, which is simple neural networks. I can only find these two mappings. So the hypothesis is that there's a huge inductive bias in the hypothesis space, which is neural networks. Convolutional neural networks can't fit any possible function, and the only functions they can fit that are cycle consistent tend to be the ones we consider meaningful. Okay. So that's the hypothesis. Of course, this is not going to be like a proof by any means that horses will map to zebras in the way we showed, but it suggests why it found that mapping, which was a simple mapping, just add stripes, as opposed to finding a different mapping, which would be take the horse, erase it, and draw a completely new zebra facing a different direction. That would be a much more complex function to learn. And the class of models which we're fitting, which are neural nets, tend to only be able to learn relatively simple functions, and there might be other kind of priors, regularization, inductive bias that will naturally make it so that they'll find the simple solution as opposed to the complex solution. Okay, this is still an open question, how much this maps onto reality. People have also been trying to understand the cycle loss as a way of something that will encourage the mapping to be simple. I said that if you perfectly optimize the cycle loss, then you get a bijective mapping, and that's one kind of relatively simple mapping. But if you don't perfectly optimize the cycle loss, because it's this soft constraint that says I should arrive near where I started if I go through the loop, well, what does it mean to be near? Well, one way to understand that is that cycle loss will actually upper bound the conditional entropy of the mapping. The conditional entropy is saying that how much uncertainty is there in the mapping, in this case, from Z to X. So, these one-to-one mappings, the two on the right, have low conditional entropy. But if I half the time mapped Z1 to X1, and the other half the time Z1 to X2, there'd be more uncertainty. So deterministic mappings have low conditional entropy. Stochastic mappings have high conditional entropy. So we're going to tend to find these deterministic mappings, and the cycle loss can be understood as something that will be an upper bound on the conditional entropy of the mapping. So one more way of understanding the cycle consistency loss as a kind of simplicity prior. Okay, so now I want to conclude with talking about what is a cycle GAN or this domain mapping actually useful for. Horses and zebras, it looks really cool, but what's the point of this? And I think it's actually has a lot of really interesting applications that are practical. And the general idea is the idea of domain adaptation. So domain adaptation is the problem of doing this domain mapping from the set of horses to zebras. But more often, what it will be used for is taking a classifier that was trained on one domain and applying that classifier to another domain. So you could train a classifier on your digit recognition problem like MNIST, and then you want to use that classifier. The post office wants to use that classifier. It was trained on these MNIST digits, they want to use it on the actual data in the wild. How can you adapt the MNIST trained classifier to work on data in the wild? And one of the big ideas here is that if we have a source domain on which we trained and we want to apply our model to a target domain, maybe we can try to map the source and target to one common domain and just train the model on that domain. And you may start to see how this is related to adversarial learning because we have two domains and we want to map to a space where you can't tell them apart, right? So again, we previously were mapping horses to zebras such that you can't tell the output zebras apart from the domain of zebras. Here, you can apply this more broadly. Okay, but let's make it a little bit more concrete. We're going to look at the problem of sim to real. So this is the problem where I want to train a vision algorithm in a simulation in the video game GTA, such that I can then apply that out on the streets. And probably not a good policy, but this is one of those problems that people work on. We want to train in GTA and then use that to drive our cars around. Okay. Yeah, not a good idea, but people do it. Okay, so what you do is we have simulated data. The simulated data comes in a really nice format, which is these input-output pairs, because in simulation, we know the location of every object, we know where the cars are, we know the labels. It's all up to us because it's simulated. And we want to apply this now out on real streets in this cityscapes data set. And we don't have labels in the wild. We want to train a classifier or an object detector that works on simulated data and apply it to outdoor photos on the street. So what you can do is we can take our GTA photos, we can use CycleGAN to map them to the appearance of our other data set, our outdoor photos in the wild. Okay, so we have our set of simulated data, we have our set of real photos, we can reason about the stylistic differences and learn this mapping from one set to the other set. Just like we were mapping horses to zebras, now we're mapping simulated data to real-looking data. Okay, so now what we do is we can simply take our synthetic training set, change the appearance of the photos in the synthetic training set to look as if they were natural outdoor photos. And this gives us kind of synthetic hallucinated training pairs of outdoor photo plus label map. Now we can simply train a object detector on that hallucinated data. Okay, so we take CycleGAN to change the appearance of our simulated rendered scenes to look more like natural outdoor scenes, and then we use that to train an object detector on the synthetic data that will apply to realistic looking photos. Okay, so this is why you actually might care about these things, because they allow you to train on simulation and then basically reason about the differences between the simulation and reality in order that your model will transfer to reality. One more example of where you can apply this is on medical data. In medical data, we often have a lot of different scans like MRIs, CT scans, but we don't have paired data. We don't have a single patient that's been scanned in multiple ways at the same time. But we know what MRI scans look like. We know what CT scans look like. We can reason about the differences between those two domains, use our CycleGAN model to predict what an MRI scan would look like if it had been done instead with CT. And that can be trained just by having a lot of CT scans, a lot of MRI scans, and trying to perform this adversarial mapping. And so, there's a lot of medical research now trying to use this. It's a little dangerous because GANs are still imperfect and they hallucinate and they do all kinds of bad things. So this is not quite ready for clinical use, but I think it's, it points to the direction of what this actually would be good for. Okay, so I've talked about three perspectives on GANs. One is that they're doing a kind of structured data prediction problem where the discriminator can be understood as a learned structured loss. Two is that you can think of them as implicit generative models that learn a way to sample from a data distribution. that they're trained on, and the other is their way of mapping between two domains. Those two domains could be the random noise domain and the domain of ImageNet photos, or it could be the domain of CT scans and MRI scans. Okay, so thank you, and open for questions. I think we have maybe a couple minutes. Yeah.
You talked a lot about images and I guess videos. Can you talk a little bit about how some of these techniques apply to some things that are not take on that sort of structure? I can imagine like speech might be pretty easy, but
Yeah.
move beyond that.
So any kind of continuous signal tends to be relatively easy. A harder kind of case is discrete data, like text or symbolic data. And yeah, there's a number of techniques for dealing with that. One is that you map the symbolic data to a continuous embedding. So there's like Word2Vec is a way of doing that on text. Other ways are you change kind of the modeling architecture to be able to represent discrete data better, so it's not just like a convolutional network. But it is a hard problem because discrete data, if you output like a continuous representation of discrete data, it will look obviously fake because the discrete data was crisp, and the continuous interpretation might not be integers; it might be floating point numbers, and it becomes easy to identify that as fake. Whereas if I have the generator just output discrete data, now it's not differentiable, and I can't do differentiable learning. So that's definitely one of the harder areas. But there's a whole family of techniques for optimizing neural networks that output discrete symbolic information. So reinforcement learning is one domain that deals with this. But yeah, anytime you have something that's like a continuous tensor, like just this, the space of real numbers, RD, it's that seems to be the data that GANs work well with. Yeah, question?
Do you think this corresponds to representations in the brain or the actual
Yeah, I think it's a really interesting question. Does our brain do any kind of adversarial training? So, yeah, unclear. I would say that one really striking thing is that the images that are produced by a GAN tend to look perceptually real. And this suggests that whatever the brain is using to measure realism is somewhat similar to what the GAN is using to measure realism. The images output by a GAN have high error in an L2 sense. So in a least squares sense, the images output by a GAN are worse than the images output by L2 regression, right? L2 regression is going to minimize the squared error. And so GANs don't minimize the squared error, so they produce things that are worse according to least squares regression. If our brain is measuring perceptual quality as something like the least squares error between the image and what you expect, if you're predicting the future and we predict something and the future turns out differently and our brain's saying like surprisal is based on L squared, least squares error, then you would expect that an L2 regression model would make things that we like more, that look more perceptually real or plausible, and that's not the case. So whatever the GAN is modeling seems to be getting at what the brain is modeling. I don't know if the brain is doing it adversarially or otherwise. Yeah. Yeah. Yeah, so I didn't really talk about all of the kind of architecture and what this like class of neural models is, and that's also important. But in most of the models that's presenting, they were, like 10 or 20 layers, convolutional neural networks. All the cyclogen results are with ResNets. So if you guys are familiar with that, the paired data, the Pix-to-Pix models were with what's called a UNet. But these are pretty standard, like image-to-image convolutional neural networks. Yeah. Okay, one last question? Yeah, in the back. How do you stabilize the output on video? So all of this was just on images, but on video, there's also been some papers. And one thing you can do is the discriminator will look at adjacent frames, and it will penalize if the adjacent frames are flickering or unstable. So there's a pretty cool project which extended this to videos called Vid2Vid from NVIDIA. And you can do all the same applications, but on videos, and they look smooth because the discriminator is looking at a space-time cube and penalizing if that space-time cube has too much flicker or instability. That's one way to do it.